Let's take a look at another example. In this case, we see our circuit has two voltage sources, and we're going to see how we deal with that, whereas our previous circuit had a current source, and that ended up being pretty easy because when we were applying KCL, we just used the value of that current source. So what we want to do in this example is find our current through this 2 ohm resistor in the center right. So we're going to follow the same steps that we had developed previously. So recall step 1 was to identify all of our essential nodes. Again, just like the previous example, we have 3 essential nodes. Notice we have one non-essential node over here in the top left. Using the same logic that I did previously, we can see that this node in the bottom has 1, 2, 3, 4 elements connected, whereas each of our other 2 nodes only has 3 elements connected. So let's go ahead and choose that bottom node to be our reference node. So I've labeled that with that arrow. Our next step is then to define node voltages. So we have 2 node voltages. Again, somewhat arbitrarily, I'll just call this node voltage V1. We do have to make that negative at the reference node, however. Similarly, I've called this node voltage V2, again, negative at the reference node. And same as we saw in the previous example, we know that we are going to have N sub E, where again, N sub E is the number of essential nodes. So in this case, we have 3 essential nodes. So 3 minus 1 gives us 2. So we expect 2 equations to solve simultaneously to get our V1 and V2. And then from there, we can find the current through that 2 ohm resistor. So the next step, now that we have defined our node voltages, is to apply KCL at each of our essential nodes that are not the reference node. And again, we're going to use KVL and Ohm's law to relate those currents back to our node voltage. So starting with our node in the top left here, which I've colored in that orange color, just like the previous example, we can define 3 currents leaving. So I'll define I1 leaving out the left, I2 leaving out the bottom, I3 going out the right. And again, that's just sort of the convention. And so what we could see is we could use the same techniques we had found previously to get an expression for I1 in terms of our V1 and our 14 volt and our 4 ohm resistor. We could use V1 and the 3 ohm to get an expression for I2, but we run into an issue over here where we only have this voltage source between node 1 and node 2. So we don't know how to define that current I3. So the way we are going to get around that is we are going to define something called a supernode. And so essentially we're going to combine what was previously our node 1 to the left of the 6 volt source and our node 2, which was to the right of the 6 volt source. And now everything in this dashed red line we're going to consider as one node or a supernode because it is enclosing more than one essential nodes. And we're going to just continue the process that we had defined previously in our steps for node voltage method analysis, but now we're just using this supernode. So I'm going to now define 4 currents because we have 4 elements connected to our supernode. I1 going out the left through the 4 ohm resistor, I2 going out the bottom through the 3 ohm, I3 through the 2 ohm, I4 through the 6 ohm. And again, we're going to use KVL and Ohm's law to relate all of those currents back to the node voltages. So here, again, I've made our circuit smaller up in the top right so we can write our equations. So if we're applying KCL at this supernode, we again see that all of our currents are leaving. So the sum of the currents leaving is I1 plus I2 plus I3 plus I4. There are 0 currents entering the supernode. So we set that equal to 0, right? Sum of currents out equals sum of currents in. So on the left side, here is an arrow indicating the direction that I'm going to do my KVL. Just like in the previous example, because I1 is going from right to left, I will define my voltage polarity such that I1 is going through a voltage drop, so positive on the right, negative on the left. And now when I do my KVL, I can say this voltage indicated by the red polarity is equal to V1 minus 14. I take that voltage V1 minus 14 and I divide it by my 4 ohms, and that's my current I1. So again, I've used KVL and Ohm's law to get my current I1 in terms of our node voltages. The other three are relatively straightforward because one side of the node we're looking at, our I2 is flowing from our supernode down to our reference node. So we simply just use Ohm's law. So here for I2 we have V1 over 3. For I3 we have V2 over 2. And for I4 we have V2 over 6. And so that's reflected in the second, third, and fourth terms here. Again, that's equal to 0. So what I've done here is I've multiplied this by the least common multiple of these denominators. So we have 4, 3, 2, and 6. So I have multiplied this by 12. So both sides of that equation, but of course 12 times 0 gives us 0. And we end up with this. Like I mentioned, personally, I often will find I make math errors going from this middle equation to this bottom equation. So you can just keep these terms as fractions and factor that way as well. Once we have this, we then want to collect our terms, and we end up with 7v1 plus 8v2 equals 42. Okay, so there is the equation for our supernode, but if you recall from a previous slide, we said we need two equations, right? We said we had three essential nodes, so 3 minus 1 is 2 equations, but we can't just move over to node 2 and do an equation for node 2 because we've already accounted for those currents that we're leaving node 2. So it turns out we're going to get our second equation from sort of looking inside of our supernode. So let me just show an excerpt here of the circuit. Again, we're looking inside the supernode. So what I have over here on the left is essentially our node 1. On the right is our node 2, and we can see that because I've got my V1 and my V2 here. And so what we're going to do now is we're going to use KVL inside the supernode to relate that voltage source inside the supernode to our external node voltages. And so what we can see, again, I've drawn this in a clockwise direction. So we could say -6 equals V2 minus V1. -6 plus V2 minus V1 equals 0, move the 6 over, and we get 6 equals V2 minus V1. So of course, we could have, again, started at any point and gone in either direction doing the KVL, and you should end up with the same result here. So here is our second equation. Again, we note it has our two unknowns, V1 and V2. So now we're at a point where we can take our two equations. We have now a supernode equation and what I'll call a inside the supernode equation. And we're going to put that into our matrix form. So we have, again, the first row of our coefficient matrix is the coefficients from our first equation. So in this case, 7 and 8. The second row of our coefficient equation is, our coefficient matrix rather, comes from our second equation, in this case, -1 and 1. We have our variable matrix, V1 and V2, our two unknown values. And then we have our constants, 42 and 6. Again, we need to make sure that the 42 is in row 1 because the 7 and 8 are coefficients from our first equation. So then we solve for that. So we say our variable matrix V1, V2 is equal to the coefficient matrix inverted times the constant matrix, and we get -0.4 and 5.6. Again, because we kept everything in terms of amps, ohms, and volts, we know that these answers are going to be in volts. So we have V1 is -0.4 volts and V2 is 5.6 volts. But of course, we weren't asked to find either voltage V1 or V2. We were asked to find this current through our 2 ohm resistor. Now we can simply use Ohm's law because we know voltage V2, we know it's a 2 ohm resistor, so we can say that that current is V2 over 2, 5.6 volts over 2 ohms is 2.8 amps. So we had to use that supernode because of how we defined our reference node on the bottom. What I would encourage you to do is try to rework this problem and define our reference node on either side of that 6 volt source. So let's say we choose this node, was our node 1, to be our reference node. And what you're going to see is if you do that, you won't need to use the supernode situation or supernode technique. So anytime you see a voltage source by itself between two essential nodes, that's when that is potentially an issue. But you can avoid that if you define the reference node as being on either side of that voltage source.